This talk today I present a statistical model for approximating working set sizes of multi-thread programs running on multi-core, multi-socket systems. The working set of an application is a measure of a dynamic. Okay. I'm defining working set of an application. It's a measure of it's a dynamic memory demand in an execution window. And we can define working set size as multiplication of the number of pages referenced over a time interval with the respective page sizes, because modern operating systems such as Solaris allocates different page sizes based on memory access patterns of the applications. And the working set information has been used for modeling resource sharing among the concurrent tasks of applications, as well as working set information has been used in Linux memory management, like especially page replacement algorithms. Therefore, knowing the information of working set size of multi-thread programs is very useful for effectively allocating resources. This work was started as developing a simple utility for measuring working set size of multi-thread programs running on Spark Solaris servers. And this utility has been used by several teams at Oracle for effectively consolidating Java applications on Oracle Cloud servers. And various techniques are proposed based on simulations and program traces for approximating WSS. However, most of the techniques are evaluated for single-threaded programs on machines with very small number of cores. And also, we can measure the actual accurately working set size of a multi-thread program on Spark running Solaris, as the Solaris provides this information through the proc file system. However, it's very expensive. For example, we measure the working set size of 20 multi-thread programs from parsec and spec-OMP benchmark suits. And the overhead is very high, ranges from 80 milliseconds to 2.5 hours, just to measure to compute the working set size of multi-thread programs. Although using these techniques, we can approximate working set size or we can measure the working set size, but the overhead is very high, so that they're not appropriate for dynamically optimizing the resources. To elevate this problem, in this work, we present a methodology for developing simple and robust models for approximating working set sizes of multi-thread programs with negligible overhead. However, characterizing working set size of a multi-thread program running on multi-core, multi-socket systems is a challenging problem. This is because there are several factors affect WSS, and also it varies from application to application. For example, for these 20 programs, the range is from 4 megabytes to 21 gigabytes. In this work, the basic idea we used to characterize the working set size is to identify first important factors that correlate with the WSS. And we use statistical models based on machine learning for characterizing the WSS. Therefore, first I'll discuss identifying the factors that correlate WSS of multi-thread programs. Next, I'll present a methodology for developing simple and robust models for approximating WSS. And finally, I briefly describe work in progress scheduling technique, working set-aware thread scheduling. To identify the important factors that correlate to working set size, is first we studied 20 multi-thread programs from parsec and spec-OMP. These programs are based upon pthreads, and they stress only CPU and main memory. And we use a Spark T44 running Oracle Solaris 11. And resident set size is how much memory currently the process has in the main memory. Although resident set size is strongly correlated with working set size, but it is skewed because it also includes shared libraries and also other types of memory. For example, when we measure the RSS and WSS of application from parsec phase sim application, you can see that there is a significant difference between RSS and WSS. X-axis is time, and Y-axis is the main memory in megabytes. And another application, for example, fluid animate from parsec. As you can see here, while RSS is steady along with the time, WSS varies a lot along with the time. Therefore, although RSS is correlate with WSS, it's not sufficient to accurately approximate WSS. And also, we observed that number of threads significantly affect WSS. Therefore, they correlate with WSS. For example, we ran image processing application from Spec OMP 2012 with a different number of threads on Spark T44. As you can see here, number of threads correlate with WSS. And also, there is a difference between RSS and WSS. Therefore, RSS and threads correlate with WSS. And we know that we use TLB cache for speeding up the translation between virtual addresses to physical addresses. So TLB reach is defined as a number of TLB entries multiplied with base size. TLB reach is very critical for achieving high performance for programs running on multi-core systems. For example, if the working set of a program is not covered by a TLB reach, then it results lots of TLB misses, and it degrades the performance of the application. Therefore, TLB miss rate is correlated with WSS. And we also observed an interesting thing is that specifically multi-thread programs with pure data parallelism, when we run this program with relatively more number of threads on multi-core, multi-socket systems, they exhibit lower TLB miss rate compared to running them with smaller number of threads. This is because when you run the program with relatively more number of threads, thread schedulers try to distribute the threads across the sockets of multi-core, multi-socket system. Therefore, threads will get an opportunity to use all the TLB cache available in the system compared to running the programs with small number of threads. Therefore, in other way, number of threads is correlate with the WSS. And modern operating system schedulers migrate threads from one core to other core to balance the load. And thread migration leads to affects data locality and last level cache miss rate. Therefore, last level cache miss rate is correlated with the WSS. Therefore, we identify that RSS, TLB miss rate, number of threads, and LLC miss rate are the factors, initial factors that correlate with WSS of multi-thread programs running on multi-core, multi-socket systems. To develop the models, we need to collect the training data. That means values of these factors by running different programs with different number of threads. Therefore, we run these programs with a different number of threads, 16, 32, 64, 128 threads on Spark T44. And we gather these input values, like input parameter values. I call it as predictors. RSS, number of threads, TLB misses per instruction, TLB misses per second, as well as last level cache misses per instruction, and last level cache misses per second. So these 6 are the initial predictors or initial input parameters, and the target parameter is WSS, working set size. So we ran these 20 programs with 4 different number of threads, and we collect totally 80 data points, and each data point is a 7 tuple. 6 are the input parameters, and the final 7th one is the target parameter, that is WSS. And one more important thing is that we have seen there are 6 initial predictors. But to balance the prediction accuracy and the cost of approximation, we need to find the important predictors among these 6. For that, we use forward and backward input selection techniques based on Akaike information criteria. Basically, it offers a relative estimate of information lost when you used a model that represents the process that gathers data. And also, it discourages the overfitting problem. Overfitting problem means like if you add more number of parameters to the model, it always gives you a good fit of the model. And also, it also avoids the multicollinearity problem. Multicollinearity is a statistical phenomenon where in a regression model, 2 or more number of predictors are highly correlated. So what is the problem with this? The problem is that the estimate of the model will be very erratic with a slight change in the data as well as the model if the predictors are very highly correlated in the regression models. So by using the AIC techniques, we can find the important predictors. so that we can consequently we can avoid the overfitting problems as well as the multicollinearity problem. That means what we are doing is that we are making the models more robust to the outliers in the data. And using these techniques, we identified that among the 6 predictors, RSS and TLB misses per instructions are the most important predictors for WSS. So using these 2 predictors, we developed 3 popular models: linear regression model, k-nearest neighbor with 2 neighbors, which gives, because that's giving the best performance, and regression tree, like it's kind of a decision tree. And for model selection, basically we wanted to select the best model among the 3 models: linear regression, k-nearest neighbor, and regression tree. We used a 10-fold cross-validation test. Basically, in this 10-fold cross-validation test, we divide the data set into 10 parts. I have shown that we collected the 80 data points by running 20 programs with 4 different number of threads. So we divide the 80 data point set into 10 parts, and the function approximator is trained for all the partitions except the one partition, which is predicted. We predict that the remaining the partition. And we used normalized root mean squared error for measuring the prediction accuracy. As you can see in the table, although all the 3 models are performing well, more than 85%, but KNN is the best one, which exhibits around 96% prediction accuracy for WSS. Therefore, we use KNN as a WSS model. And also, we evaluated this KNN model, WSS model, with real workloads. For example, data cache benchmark from CloudSuite, which is based on memcached on SpecJBB 2005. And it results like the prediction accuracy is like 93% for memcached benchmark and 88% for the SpecJBB 2005. And the overhead of this KNN model, WSS model, is negligible compared to the existing techniques. For example, that is just within 24 microseconds, you can get the WSS of the multithread program running on multi-core, multi-socket system. Compared to the existing techniques, for example, on Solaris, to measure the working set size, maximum you need to spend like 2.5 hours among the 20 multithread programs. Therefore, the model that we developed in this work is, the overhead is negligible. We can effectively use this for dynamically optimizing the resources. So I'll present the overall approach summary. So first of all, we need to identify what are the important factors that correlate with the target parameter, for example, WS. Once you identify the factors, initial factors, you develop a linear regression model with all the reasonable factors, I call predictors, of WSS using training data. You gather the data and you develop a linear regression model. Then you need to identify the important predictors because you wanted to avoid overfitting problem as well as the multicollinearity problem. So you can use AAC techniques or any other techniques which is for this kind of like selecting the important predictors. Once you identify the important factors, develop different models with these predictors, and then use cross-validation test using both on training data and testing data, and select the best model that gives the highest prediction accuracy. Next, I'll briefly describe our work in progress scheduling technique called working set-aware thread scheduling. Actually, scheduling threads of a multithread program running on, for example, Spark T44. Spark T44 has 256 hardware thread contexts. And now we are using, for example, Spark T8, which has like 1024 hardware thread contexts. Scheduling threads of a multithread program on large-scale multi-core systems is really challenging problem. In a high level, you can divide the 2 ways you can schedule the threads. Either group the threads on fewer processors or spread the threads uniformly across all the sockets of multi-core, multi-socket systems. For example, if you consider Linux scheduler, even if you give 4 threads to Linux scheduler on a Spark T44, which has like 4 sockets and 256 hardware thread contexts, Linux scheduler will allocate 1 thread to 1 socket. That means by default, Linux scheduler uniformly distributes the threads across the sockets. However, Solaris and Spark, initially it starts grouping the threads, but once it reaches a threshold in terms of the number of threads, it's trying to spread the threads across the sockets. However, these 2 scheduling algorithms are not ideal for all the applications. For example, we observed that on Spark T44, on multi-core, multi-socket system, not only Spark T44, we also tried on x86, AMD Opteron processor system, 4-core, 4-socket system. Programs with small working set sizes is getting better performance when you group the threads. That means when you use fewer processors. For example, we ran a border track program from Parsec benchmark suite, which gives 31% performance improvement when we group the threads. That means when we group the threads on fewer processors compared to uniformly spreading the threads across the sockets. And also, programs with large working sets, we observed that by spreading the threads across the sockets, we see better performance improvements. For example, Stream Cluster from Parsec benchmark suite, which has very large working set. It achieves 24% performance improvement. Therefore, okay, if you consider even Linux thread scheduler and Solid thread scheduler, basically they consider number of threads as important factor to schedule threads, basically to allocate cores to the threads, but which is not sufficient for emerging multi-thread programs. We need to consider workload characteristics, for example, WSS and other for example, lock convention, so that we can effectively schedule the threads on these large multi-core systems so we can achieve the better performance. And in conclusion, in this work, we identify important factors that correlate with WSS of multi-threaded applications running on multi-core, multi-socket systems with a large number of cores. And also, we present a methodology based on machine learning for developing simple and robust models for approximating working set sizes of multi-threaded programs. And the model overhead of the model is very negligible, so we can use it for effectively allocating resources on large multi-core systems. And finally, I would like to, I'm really thankful to these guys. These are nice people and kind people. They helped me throughout my work. And also, thank you very much for you guys for your time. Thanks.
One thing I somewhat question is whether working set is so important these days because we have such large memories that very often everything fits. I'm wondering if you've thought much about whether these same techniques might be usable in terms of asking what should be held in cache. For example, my group has done a bit of work with Facebook looking at their edge caches. There's always this question, an object goes past, should you hang on to it or not? Or maybe other kinds of settings, such as video playback. So, are there other contexts where this type of machine learning and this approach might be usable?
Definitely. For example, memory allocation aspects. For example, when you are scheduling virtual machines on cloud, definitely these kind of techniques are very useful. I heard VMware are using somewhat similar ideas for not only effectively allocating virtual machines, and also finding the failures, high availability aspect also.
And do you think that in these other settings you get a similar finding that relatively small subset of the available metrics really are adequate to train the learning method and are the dominant ones to focus upon?
I believe that, yes.
Hi, Björn Muk of MPI SWS. A quick question. You mentioned that a certain amount of error. Do you underestimate or overestimate? And for the application that you're interested in, does it matter?
You mean the error?
Yes, when you predict the working set size.
It doesn't matter.
Doesn't matter.
Doesn't matter for this work, yes. I see that, for some applications, the model underestimated. For other applications, overestimate. I see that both. Because the range, if you see the range of the working set sizes of the applications, 4 megabytes to 21 gigabytes. It's a huge range.
All right, thanks.
I have one question that I will just, sorry, I won't use the mic, but can repeat it. So you evaluated a bunch of models and you said they were all good because you had accuracies in the high 80s or low 90s.
Yeah.
How do you know what sort of accuracies are acceptable for the kind of applications you need these models for?
You're right, actually, very good question. Depending on the application, for example, what we observed, what I have seen in the literature, if the model, depending on the area also, for example, especially computer science workload characterization, I have seen that if the model has better than 80% prediction accuracy, think that it's a good prediction. I don't have a scientific reason for that.
Okay, Frank Belosa from KIT. The Spark architecture uses the translation storage buffer, which is a cache for the most recently used page mappings to speed up the TLB miss. So couldn't you just look into this TSB memory, which is 2 or 4 megabytes, to identify the working set, which are those pages which were referenced most recently, and then you find between different sockets pages that were used in both sockets, and then you can do better migration decisions?
Pretty good question, but the problem is that the page size is not uniform. If you take Solaris, based on the application and also based on segment of the application, it will allocate different page sizes.
But this is in the TSB entries. So you see in the TSB entries the page sizes, and you just analyze this piece of memory in the kernel.
Maybe, probably.
Have you modified the kernel for this tracing?
No, I use like proc file system.
Okay.
It gives the page sizes as well as the number of
Okay, yeah,
pages.
for the TSB you have to modify the TLB with handler.
Yeah.
Okay, thank you.
Thank you.
Let's thank the speaker one more time.